just a couple announcements first. Sorry I wasn't able to make it back yesterday. My flight was canceled, so I had to stay where I was for longer than it allowed me to get here in time. But to make up for that, I'll be coming in on Friday and recording a lecture so we stay on schedule. Of course, no one's required to be here for that. I'll just ask that you watch it before Monday, before class, sometime over the weekend. Okay? So, sorry about that. Another thing you might notice is that our schedule has drifted a little bit from what's on the syllabus. And that's just because I didn't account for the Mondays that we would be missing. So we'll make up a lot of time next week, which is a full week, quote unquote. Then I wanted to remind you also that exam 3 is, what date is next Thursday? Is that the 10th? Yeah. Right. 6:10, same deal. Beginning part of class will be review, and then we'll take the exam. 2:10, 3:10. My anticipation is that we'll finish up through chapter 8 by next Tuesday. And that's what will be covered on the exam. Okay? So let's just say chapters 5 through 8, or whatever we get through. By next Tuesday. Okay, in case we don't get all the way through the end of chapter 8. It's okay. Sorry, Keenan asked the question here. Will it also be live, in case you wanted to be there, attend at the time? Yeah, actually. I'm just gonna use the usual Zoom link for lectures, because that automatically makes a recording upload to the cloud. I feel like that would be the easiest thing.
We'll also be at the same time
though? Yep. I'll do it at exactly the same time, but obviously we're not scheduled to meet on Friday. By all means, don't feel any pressure to come, that's fine. But if you do want to sign on to the Zoom during the normal scheduled time, I'll be here. Okay, good. Oh, right, and of course, review/practice exams. Sent out tomorrow night. And obviously this will cover, the practice exams will have some material on them that we haven't yet covered. But you can start just on whatever material we have covered. Okay, now the last where we left off is I asked you to try some problems from chapter 5, right? So, are there any questions about any of those homework problems? And let me see, there, yeah. Okay, so Keenan asked for 5.1, 5.8, and 5.9. Okay. Right. So, here's 5.1. We have two congruent triangles, ABC and DEF. And we're actually given coordinates for all these points, okay? So let me just, draw a picture. Let's see. All right, so this has A at the origin. B is here along the x-axis, and C is way up here along the y-axis. So we have this triangle, right triangle, and then what do we have? D comes at 4 and goes up 2. Right? Here's D. E is over here. And F is all the way out here. Okay, so of course, again, you have to take my drawings with a grain of salt, but hopefully by looking at where the right angle goes, you can see how these triangles are congruent. Yeah? Okay, so the question asked us to find the equations of the lines such that we can determine the isometry that takes the triangle ABC to the triangle DEF, F. And remember, what we did in class at the end of last week is show that there are at most 3 lines for which we find the equation. That we can express that isometry as a product of reflections. Okay, so here's what we know. There is an isometry taking the triangle ABC to the triangle DEF, and also, let's call it alpha, I should say. Say alpha. Also, we know alpha is a product of reflections, right? And L. Or some of these reflections might be the identity, depending on if after one or the other of the reflections, 2 of our vertices get mapped to what they should. Okay? So I'll write that down. Where possibly some of these reflections are actually the identity. Okay? All right. So how do we do this? Basically, what you want to do is go back and look at how we proved that this is always the case, with the possibility of some of these being the identity. Okay? So, first of all, we want, let me get a different colored marker here. We want A to go to D, right? we should define the perpendicular bisector of the line segment AD. Okay? So we want A to go to D. So what we do is construct the line L which is the perpendicular bisector of the line segment AD. Okay, and that will be our first applied reflection. Okay? Okay, so how do we determine the equation of L?
Take the negative reciprocal slope.
Yeah.
And then use the midpoint as a point that you know is on the line to find the intercept.
Yeah, exactly. Right, so just to recap, since L is the perpendicular bisector of A and D, by being perpendicular, it has to have the negative reciprocal of the slope of the line segment AD. And then we know the coordinates for A and D, so we can calculate the midpoint. And then plug that in to find the y-intercept of the equation of the line L. Good. So, line segment AD has slope. What's A? What's D? 2 minus 0 over 4 minus 0, or 1/2, right? So this implies L has slope -2. So we know the midpoint of AD is on L. So plug that in to y equals -2x plus b, where lowercase b is my y-intercept for the line L. Okay, so what's the midpoint?
1.2.
Is just 2 comma 1, right? We plug in this point into this equation, and what does that tell us b is? I got 5, right? Plugging in gives b equal to 5. L as equation. Y equals -2x plus 5. Okay, now, the next thing we want is that B should go to E, right? If I start at the right angle in the triangle ABC and then go to the next vertex in this order, then I get to B, right? Same if I start here at D with the right angle and go to the next vertex, I should want to have E. Okay? So, I really should have drawn this better, but, well,
The image of B, right?
sorry?
The image of B first, right?
So, yeah, well, the point is that,
Oh, it's already there.
yeah, it's already there.
Oh.
This line L is the perpendicular bisector of the line segment BE. Okay? Now, just looking at that gives you a hint. That's not a proof, right? So let's just quickly go through the verification that the perpendicular bisector of BE is again this same line L. Now, notice that the perpendicular bisector, remember, I'll just write PB for that, of the line segment BE is just L. How do we verify that?
Find the slope.
Yeah, we do just exactly the same thing that we did for the line segment AD and computing its perpendicular bisector. Okay? So, right. The slope of the line segment BE is, okay, so now we take, sorry, I didn't write down the coordinates on the board. So now we take -2 minus 0 divided by 1 minus 5, 1/2. Okay, that's a good start, right? It at least has the same slope. So now we plug in midpoint of BE into the same linear equation, not knowing the y-intercept. Okay? So, surprise, you get 5 again. So it's legitimately the same line. Okay? Now, I just want to say, how we interpret that now is, okay, so we explicitly described L. Now the next reflection that's supposed to take B to E is trivial. It's just the identity, because we already took B to E by operating the reflection L on this triangle. Okay? So I'm erasing this board just because I want to keep the picture up. Okay, so those computations we just made imply that sigma sub m is equal to the identity. Okay? So then, finally, what do we do? So now our final line, if you go back and look at the proof of the fact that any isometry can be expressed as the product of at most 3 reflections, the last line we'll reflect about is the line defined by D and E. The 2 points of the triangle, the 2 vertices of the triangle that you've already mapped where you want them to be. Okay, so this is, in our notation here, the line N. Okay? And that's not totally surprising, just visually, if you look at C to F, this is kind of, you kind of see it, right? Again, it's hard to tell because of imprecise drawings, but, okay. So, let me just say, after this, after you go back and look at that step of the proof, I feel confident that we can all write down the equation of this line N. I'm not going to do that calculation, but you know 2 points on it. Should be good. Okay. So finally, let N be the unique line through the points D and E, then alpha equal to sigma n sigma L, as we've defined here, gives us our isometry. Or let me write this out explicitly, right? I have an iota in the middle here, right? But of course, that just disappears. Okay, so yeah, kind of a lot of work, but the steps are all outlined in the proof. You're just doing it for a specific example here. And you know, I think this is a good thing to go through together, because you know, this is kind of the idea of what you want to do. Draw a picture, get some intuition, and then try to do some calculations. Okay? Okay, so now let's discuss 5.8. Yeah. So 5.8, we have A, B, C, D. Is congruent to E, F, G, H. Rectangles with the distance from A to B not equal to the distance from B to C. What is this condition telling us?
It's not a square.
It's not a square, right? They're rectangles that have two pairs of equal length sides that are not the same. Okay? So, now, the question is, how many isometries take ABC to EFGH? Okay, so we didn't talk about isometries preserving congruent rectangles, right? But what we do know is that isometries preserve congruent triangles, right? So we can just chop these rectangles in half across the diagonal in the correct fashion. Okay, so first, cut ABCD into two triangles. A, B, C, and what? Why don't we just say CDB? Right? That's just cutting along the diagonal. So we know there's exactly one isometry sending triangle ABC to triangle EFG, right? There is exactly one isometry sending triangle ABC to triangle EFG. Okay, and that's actually enough. That determines where our image rectangle ends up, right? There's only one point that you can stick onto this to make it a rectangle that's congruent to the original rectangle. Okay? So this determines sending A, B, C, D to E, F, G, H. Now, here's the tricky part. So we did this together. What's the isometry group of a rectangle which is not a square? It's the Klein 4 group. So, in other words, we can tack on any symmetry of that rectangle and get an isometry that goes from ABCD to EFGH. Okay, so let's just say this. Here's my rectangle. Okay, and let's say some isometry takes it to E, F, G, H. Right? And yeah, this is alpha. But after I do that, I can do any of the usual the symmetries, which are isometries, that preserve quadrilateral EFGH. So there are 4 isometries total that we get by composing alpha with the symmetries of E, F, G, H. Right? And remember, a symmetry is just a type of isometry. It's an isometry that preserves a certain set, which in this case happens to be this rectangle, EFGH. Okay? So that is to say, they are, first I do alpha, then I do iota. I just get alpha. First I do alpha, then I do vertical reflection. First I do alpha, then I do horizontal reflection. Or finally, first I do alpha, and then I do a half turn about the origin. Question?
Origin? Center of the...
Yeah, center. Right. Yeah. Right. I'm going to stick with this notation just because it's the notation for the...
we stick axes like that.
Right. Right. Yeah. Okay. So, really quickly, let's just look at 5.9. And then we should probably get started. So, let's see. So we're asked to prove that if sigma n, sigma m fixes point P and the lines N and M are distinct, then P lies on both M and N. Okay. So, first of all, let's just set up some notation. So let's suppose that sigma m takes p to q, and in order for sigma n to fix p, we know that sigma n of q must equal p. Okay? All right. So what does this tell us? Then sigma m of p equal to q means what? What does this mean in geometric language? In terms of the line M, what does this tell us about the relationship between the points P and Q?
Is it perpendicular bisector of the segment connecting them?
Sorry, can you say that one more time?
It should perpendicularly bisect the segment connecting P and Q.
Yeah, right. It's the perpendicular bisector of the segment PQ. Right. Means M is the perpendicular bisector of PQ. Now, remember, I made a point to say this, sigma n of Q is equal to P, means n is a perpendicular bisector of the line segment QP, i.e. PQ. Right? So, what does this tell us? For some reason, I thought that completed the proof. Why did I think that?
If they're both perpendicular bisector of other equal.
Right.
Wait.
Right. Which means.
Why are we saying that the reflection of n equals q? Yeah, or n equals p from q.
Oh, you're right. I'm sorry. Well, that's because
Because those reflections fix point P.
Right.
Right, they're not incursives. That's the point, right?
Yeah, but the fact that the composition preserves P means that whatever M sends P to,
Whatever m says, okay.
N of that has to be P. Okay? So,
Yeah.
okay, here's why this completes the proof. Sorry, I didn't write this down. So this implies M equals N, right? Which is a contradiction. So, in fact, Q is equal to P all along. It was fixed by both N and M. So therefore, we made a wrong assumption in saying that Q was not P. Okay? And P is on both M and N. Why is that?
Because it was fixed by both of the reflections.
Right, because the fixed points of the reflection,
Are the lines.
sigma n, are exactly the points on the line n. And the fixed points of the line, the reflection, sigma sub m, are exactly the points on the line m. So therefore, P has to be on both n and m. Okay? Good. So if there's any further questions about the homework from chapter 5, I think we had better address them during office hours and start talking about the material, the rest of the material from chapter 6. Okay? So, where were we? Ah, yes. So, we have all these nice results about how isometries are generated from reflections. Now, we want to take a bit of a further investigation as to the isometries that are, first we'll look at the isometries that are a product of two reflections and say something that kind of classifies those. Okay? So if you recall, and I wouldn't blame you for not recalling, it's been a while, but we defined the directed distance between two lines, right? Two parallel lines. So let me just remind you, two parallel lines, wait, I'm sorry. I should step back one half step further even. So, let me remind you again, there are two cases in studying the product of two reflections. Sigma M, sigma L. Either one, M is parallel to L, or two, M and L intersect. And this is, of course, we're assuming M is not equal to L, because if we have the product of sigma M times sigma M, we just get the identity. All reflections are involutive. Okay, so first, let's assume M and L are parallel. Let's see what we can say about the product of the reflection sigma M and sigma L. Okay? So, if M and L are parallel, then sigma M, sigma L is the translation through twice the directed distance from L to M. Okay, so remember, this is one of the last things we did last Thursday. We defined this notion of directed distance, which is a notion of distance between lines that are parallel. And we take two parallel lines, and they must have a common perpendicular line. And for the points of intersection, for that common perpendicular and each of the two lines we started with, the directed distance from L to M is the distance between those 2 points of intersection. Okay? And we drew a little diagram of this last time. Hopefully, everyone remembers that. Okay. Okay, so as such, let's draw out what the directed distance means. Let's do another pictorial representation of this. So we have the line L, and we have the line M, and we choose some common perpendicular to these two lines, which must exist since they're parallel. Okay, and so what I was saying is, if we let this point be capital L, and this point capital M, then the distance from L to M is the directed distance from lines L to M. Okay? Okay. So now let's take a point. Take K on the line L, distinct from capital L. And then we'll let L prime be the image of L under sigma sub M, and we'll take K prime equal to the image under the translation that takes L to L prime of our point K. Right, so now I'll add all this to the picture. Okay, here's the point K on L, independent from capital L. Okay, and then if I want M to be the perpendicular bisector of L and some other point, I'll just add a little length here. Be slightly more accurate. So what does that looks like about here, right? L prime, sigma M of L.
So we're starting with M,
Sorry?
or starting with M,
We're starting with both M and L.
I mean, for the reflection.
No. You'll see that it comes out in the right order once we're done. Okay. Okay. So right, I've just reflected this point over to here. Okay, and then I have some point K prime that is K translated the distance from L to L prime. Does that show up okay? Oh, should really not write so close to the top, huh? The top. Okay. Then we must have that next line, tau of k prime is equal to tau of L prime, right? Okay, so and furthermore, the quadrilateral L K prime L prime is a perpendicular bisector of the segment L prime and of course the segment K prime, right? and of KK prime. Okay, so what does this tell us? That sigma m takes k to k prime, right? Because m is the perpendicular bisector of kk prime. Okay? That k prime is equal to sigma m of k. So I'll record that here as well. Okay. Now, let's let J equal to sigma L of M. Then what does this tell us? Then we have capital L is the midpoint of the line segment JM, right? Just by the definition of reflection. And also, we also have M is the midpoint of LL prime. Right? Okay, so I'll extend this way as well to include J in my diagram. And so I have J equal to sigma sub L of M. Okay. So what does this mean? Therefore, we must have the translation taking J to M is just the same as the translation taking L to L prime. Okay? Again, my drawing is probably not to scale. So I want you to notice that the translation from L to L prime is twice the directed distance from L to M. And that should be fairly obvious from the picture, right? I'm just rotating this whole line segment around the line L.
Makes sense, because it goes through like half turn thing.
Say that again?
At that point, it makes sense to want to go like half turn algebra.
Yeah. Okay. So we have the following string of equalities, right? We have sigma m, sigma L of J is equal to sigma m of M, which is, of course, just M since capital M lies on M, which is equal to the translation that takes L to L prime of J. Okay? We have sigma m, sigma L of K is equal to sigma m of K. Remember, I chose K to be on line L, distinct from capital L. And what is sigma n of K? This is just what we defined to be K prime. And we showed in the course of our making of this diagram that this is the same as tau sub L comma L of K. And finally, we have sigma m, sigma L of L is equal to sigma m of L. Of course, sigma sub L fixed to L since it's on the line, lowercase l. We have set this equal to L prime, which by definition of tau sub L comma L prime must be equal to this translation of L. Okay? So what have I shown?
We have 3 non-collinear points for which the transformations have the same results.
Yeah, exactly. I have 3 non-collinear points, right? i.e. a triangle. And this was one of our main results about isometries, right? 3 non-collinear points determine an isometry. So, we see that sigma lowercase l must equal this translation. Since they agree on JK and L, which are 3 non-collinear points. Okay, so I know that in the course of this proof, it's like, well, how do I know what to do, what to choose, what to pick here? Like, I understand that that's kind of hard to come up with originally. But yeah, it's important that we go through them together so you get a sense of that, though. I hope it's clear by this point, I'm never going to ask you to do some hard geometric proof like this on an exam. But I think it's of utmost importance that we do these things together. Okay? Okay. So, right. Another way of writing our conclusion is sigma m, sigma L, tau L comma L prime, tau L comma M squared, right? That is, we shift the directed distance from L to M twice. Translate that twice. Okay? Okay. Good. I'm gonna give you a bunch of corollaries, a couple more theorems, and then just restate those theorems in different useful ways. It's all the same content, but sometimes it's faster to have a theorem stated a different way, depending on the use case. Okay? Here's a corollary. If there is some line B that is perpendicular to both, well, I should say perpendicular to L at point capital L and M at point capital M, then we have the following. Okay. Sigma sub M times sigma sub L is equal to, this is just what we proved, but in fact, we can express this another way, as a product of half terms. Okay, so let me just, this is dangerously similar notation, right? So these are reflections. And these are half terms. Okay, so this follows directly from the results of chapter 3 that we talked about using half terms. Okay, so immediate from chapter 3 and our study of half terms. So here's something I'll ask you to do tonight. Go back and verify this. It's just have to find the right page in the book and you'll see it immediately. Okay? So verify this. So I want to point out here that this is a very special circumstance. Okay, we're assuming that there's some line B that's perpendicular to both lines L and M, i.e. L and M are parallel. Now, that is why we're in this special situation, right? Because half turns have exactly one fixed point, right? Whereas reflections have fixed lines. Okay, so just don't forget the setup to this corollary, that this only applies to parallel lines. Okay? Okay. So, I think it must have been 2 weeks ago at this point, we showed that translations are always a product of two half terms. Right? So what can we say in a similar vein about how translations are related to reflections? Well, this is some clue as to that, but maybe we can say something a little more general.
They're parallel, it's four reflections.
Right. arbitrary translation is a product of two reflections in two parallel lines. That is, if we take an arbitrary translation, we can express it as the reflection of two parallel lines.
You just choose the line so that the direct distance is half of the translation vector.
Exactly. Pick an arbitrary line, and then choose the next perpendicular line over from the bisector that is, not the bisector, the perpendicular that is the right distance away, which is half of the distance of the translation. Yeah, good. And conversely, a product of two reflections in parallel lines in is a translation. Okay. So they're on the money. That's exactly what we'll do. Let's say all the details out together on the board. Okay? So, take a non-identity translation. Okay? Because obviously the identity translation is trivial. You can take any line and make the reflection in that twice. Okay. We'll call it tau sub L comma N. And we know that tau of L comma N is equal to sigma sub M, sigma sub L, where M is the midpoint of Ln. So then we'll set L to be perpendicular to the line, the unique line between L and N at point L. At point L. Okay? And let's say M to be perpendicular to the line defined by Ln at point M. Okay? then by the last corollary, we have a half term at M times a half term centered at L is equal to the reflection in M times the reflection in L, which then, of course, gives us our desired result. Sigma M, sigma L. Okay? So, good. Here's our next theorem. If L, M, and N are all perpendicular to some line B, then there are unique lines P and Q such that sigma M, sigma L is equal to sigma N, sigma P is equal to sigma Q, sigma N. With P and Q both, of course, perpendicular to the line B. Okay, so this is a lot like the result that we had about half turns, right? Where if we knew any 3 half turns out of 4, or any 3 points that we wanted to make half turns about out of 4 points, the 4th one was uniquely determined. This is an analogous result to that, but stated for reflections instead of half turns. Okay? Okay. So, I don't want to draw a diagram here, so. Well, I'll set up some notation. Okay. So, let's just label some points. Suppose L, M, and N intersect B at points L, M, and N, respectively. And let's let points P and Q be the unique solutions to, this is where I'm going to use that result on half turns, right? as a capital P. Okay, so in each circumstance, we apply that same result on half terms, right? For this equality, I know M, L, and N. And I'm determining the unique point P such that this equation holds. Okay, same thing here, right? I still know L, M, and N, but the ordering is just different. Remember, that was the strength of the result. It was any 3 points, and you can uniquely determine the fourth. Okay? Okay. So, for example, let's look at some diagram. Okay, so I'll have my line B, and I'll take my line L here, which intersects B at point L. I'll just take my point M here, intersects B at point M, and let's say, well, put that a little closer. Let's say point N here, my line N, right? So I just want to choose the point P, choose P, so that this is equal to the distance from L to M, right? And so I guess I should write that down. Well, so where do you choose Q? The other point on B that has length LM from N, right? This kind of gives you an idea of where the term directed distance comes from. But you can do it on both sides. Okay. Okay. All right, so then all we do is consider lines P through point P perpendicular to B, and likewise Q through the point capital Q perpendicular to B. Then by the last corollary, we have our result. Right, so very good drawing, sorry. The point is that as long as everything's parallel, if you want to remain on the same line, there's two choices. Okay? Okay. So, now, if we take 2 points, P not equal to Q, then the translation, taking P to Q, may be expressed as sigma B, sigma A, where either A or B is an arbitrary perpendicular line to the line through P and Q, and the other of A and B is just a perpendicular line to the same line through P and Q. With directed distance PQ, could have left that without a bar, but away from the first line. Okay, so I'm going to point out here, this again gives some meaning to the term directed distance between two lines. And because it has some order to it, because of the way that we compose these two isometries, we say the second line is uniquely determined. Right? And that's because of the order that these are in. Right? Let's say I arbitrarily choose A to be a perpendicular line to PQ, the line through PQ. Then if I want to construct B so that this statement is true, B has to be on this side of, this side of A, the line A. If I arbitrarily choose B to be perpendicular to the line through P and Q, then I have to have B beyond, A beyond this side, plays the role of P here. Okay? So, yeah, at first glance, it would be, it's confusing that we say directed distance between lines. But ultimately, this is why. Because composition is not commutative in general. Okay, so, Jordan asks, do you mean just PQ and not the segment PQ, or would it be with the segment line over it? Yeah, I'm looking at my notes here, and I'm not sure exactly why I wrote that. It's definitely clear what I meant, but I think you're technically right, Jordan. No bar there. Okay, good. I'm keeping honest over here. Okay, so this is just a restatement of what we did here, of this drawing. So I'm not going to say anything about the proof. Not really much to say. Okay. So one last corollary before we start talking about case 2, when we discuss the product of two reflections, when the lines that define them are not parallel, they're intersecting. But first, one last corollary, which again is essentially a restatement of what we already done. Okay, so if lines L, M, and N, all perpendicular to B, then sigma N, sigma M, sigma L is a reflection in a line perpendicular to B. Well, I mean, okay, this is just, we know this, right? For a uniquely determined line P, perpendicular to B, yeah, perpendicular to B. Well, this is the case if and only if sigma N, sigma M, sigma L is equal to sigma sub P, right? I just multiply by sigma sub N on the left, both sides of this equation. Okay. So again, really no new content here, just a different way to say the same thing. Okay, so now, what about the case when we have a product of a pair of reflections which are not parallel? The situation is pleasantly similar, but also markedly different. Case 2. M and L intersect. What can we say about sigma M, sigma L? Any guesses before we?
No one has to fix one point.
I'm sorry, say that again?
He has to fix one point, exactly.
Okay.
Right?
So it has to fix one point. I agree with that. Exactly.
Oh,
Is it a rotation?
It's a rotation. Yeah. Good. So
fixes.
So yes. Good. Let us see the way in which this happens. Okay. So let's say lines L and M intersect at point C, and the directed angle measure from L to M is theta divided by 2, then sigma M, sigma L is equal to the rotation centered at C through angle theta. Sorry, angle theta. Okay, so again, we're seeing something. Remember, we showed eventually that the product of two reflections in a pair of parallel lines was twice the translation of twice the directed distance between them.
How do you define directed angle measure?
So, what is directed angle measure?
Because like there should be two angles, right?
Yep. So it's the standard convention from trigonometry where counterclockwise is positive and clockwise is, no, sorry. Yeah, counterclockwise is positive, clockwise is negative.
So you start on L, go to the point.
That is to say, what is the directed angle measure between? It's between two lines, right? So, yeah, this is strictly a synthetic concept as far as we're concerned until there's a number attached to it. We haven't said anything about analytically determining the angle measurement based on distances.
Right. If you start at an arbitrary point on L to N.
So,
to a third point is the angle.
So, yeah, I mean, that's true. That is a way to define it, but I think the standard way of doing it is to construct a circle around the point of intersection.
Okay.
And then you can actually talk, if you wanted to, you could talk about the length of the arc corresponding to the measurement of the angle. That's the standard way. But I think you could do something like that. It's just a little less elegant because it's ambiguous which points you choose. Okay? Yeah, basically constructing the circle makes it so that you have a isosceles triangle, right? You have two radii as the two legs of the triangle. Yeah, good question. Okay. So, take a point, capital L on line L, different from C. And then what we'll do is consider the circle our favorite notation, C sub L. Okay? So hopefully drawing this diagram will make it less annoying, this notation. And let capital M be the intersection point of M. here's our line L, and here's our line M, and have our point of intersection C, and we picked some other point L on the line L, and we drew a circle. That wasn't actually that bad. And then we say M is this point, okay? And again, you can choose this point down here, but then you have a negative angle measure. And if you look back at the properties of rotation that we enumerated, that's the inverse of a rotation, right? It's the, that is to say, so I'll just put it aside here. Recall rho C theta inverse is just equal to rho sub C comma negative theta.
Isn't the negative angle, is it? Oh, you both the other options?
Yeah. So they
Okay.
so they interchange, and it's the same as
Because you're going counterclockwise.
yeah, exactly. Because if you start at L, you have to go counterclockwise if you chose this point.
Right, so you start the other side of L and.
Right. Okay. Okay. Yeah. If this is causing confusion, it wouldn't hurt to go back to, let's see. There's actually, okay, there's a very short block of text in the textbook about this. And since I only gave you one thing for homework, I'll ask you to do this tonight as well. So let me just ask you to homework. Read middle of page 40 and text starting note that row of C comma 30. Okay, it's just one paragraph. But all this paragraph says is that angles act exactly like you remember from trigonometry. That the convention dictates that we pretend we're like on coordinate axes here, and counterclockwise is positive and clockwise is negative. Okay? So quickly read that tonight. Okay, so let's see if we can finish this in the next 5 minutes. Okay, so here's the, since I chose this point M, our directed angle measure is
Okay, that makes more sense than the inverse now.
theta over 2. Yeah, okay, good. Okay. Yeah, of course, I chose to draw this line L so it would remind you of the x-axis, but it could be oriented any way in the plane, and we just look at it differently. Okay? So, ref. Now let's set L prime equal to rho sub C comma theta of L. So that L prime lies on a circle. And M is the perpendicular bisector of the line segment L prime. Okay, so I'll draw this ray here, L prime. And what I'm saying is that this is the right angle, and these two halves are equal. Right? Of course, we know that L prime lies on the circle because a rotation fixes the circle that has the same center as the rotation. Right? Now, how do we know this is a perpendicular bisector? M is the perpendicular bisector of L prime? Well, this is a consequence of similar triangles. Okay? Because we went theta to get to L prime, we know that this triangle has an interior angle theta L squared. The sides are two radii, and they share this side. Side angle side. Side angle side.
Also, angle side angle.
Yeah.
Because you define that as a right angle. Then.
Yeah. That's also okay. Okay. So that's halfway through. But essentially, let me just give you a preview of where we're going here. We're just going to show that this isometry, rho sub c comma theta, has the same value on three non-collinear points as sigma sub f and sigma sub l. So therefore, they must be the same isometry. It's the same trick that we used before, only now we're working on a circle instead of a bunch of parallel lines. Okay? Okay. So, yeah, with that, just take a look at that proof and read the middle of page 40 in the textbook. And then we'll finish this proof tomorrow. Okay?
Thank you.